Hello, so the whole point of this video that I'm going to give now is to try and give a broad overview of what is radio frequency electronics. Don't worry about the big words, just try and stay with me. It should be quite simple as long as you went to school and you followed a few of your maths lessons and a few of your science lessons. So anyway, enjoy. I hope it's interesting for you and well, let's get on with it. So, this is the title page. I don't like reading things straight out off it. Don't worry, there's going to be plenty of pictures and moving things in this presentation for you. So, these are the topics we're going to be covering. So, we're going to be focusing a bit around TVs, because that's the area that I work in at the moment. So, try and actually understand physically what's going on. How are the waves travelling through the air? How is it affected? And trying to bring it down to a level that most people should be able to understand. Okay, so let's go. So fingers crossed, I hope things will be alright, and like I said, I'll try and keep it quite simple and try not to use too many acronyms, but let's see how we go. So, what are tuners in the real world? This is what I'm going to try and explain today. So when we take our recording, and when it goes to our broadcast antenna, which is the great big ones you see on the top of the hills, and then how this is transferred through the air, this is what we're going to focus on today. How it's received by your house, that's the antenna on top of your house. And then, for example, I'm already lying to you because I showed you the waves curving through the air. That's not what happens. They actually travel in a straight line. It's the sort of thing I'm going to try and get you to think about today. So once we receive the signal, it then goes through your house, through the cabling, however it was built, the house, and finally it ends up in your television. Hence we get a nice moving signal. Okay, I'm going to explain a bit more about that now. So, do you remember these TVs? It depends how old you are. If you're around about 16, maybe not. But if you're a little bit older like me, I had one of these in my bedroom until I was probably about 16 as well. What were these? So do you remember? You used to have to turn these by hand in order to change the channel. And then later on, you get your lovely picture. But then what happens if you didn't tune it correctly? What happens if you turn it another way? You get a horrible noise. I'm going to explain to you a bit what that is later on. So, let's have a look at digital TVs. We've just looked at analog TVs, and now we're going to look at digital ones. So, take a modern type TV, let's just swirl it around so we can have a look at it. Let's look a little bit closer on this bit here, and then up in behind the plastic there will be this little module, this little bit of electronics, which don't worry about what it is at the moment. But basically, inside this, what happens is, instead of us changing the channel, this time we press our signal, our lovely remote control modern thing. It then goes through the TV and then does its magic inside of the module or inside the electronics itself. And I'm going to explain a bit more about this. So what is it? This is a magic box. I'm going to explain to you what the magic box is. Don't worry, it's not going to be that complicated. And as you can see, this is a magic box in reverse. I flipped it around. I'll explain why now. So, okay, acronyms, but don't worry, we're not going to worry about them. So we've got our MPEG-2, our H.264, our HD, our JPEG, our MP3, our whatever the hell it's been recorded in whatever format. And this is being transferred through the air as ones and zeros. Let's not forget, in the digital world, it doesn't matter what it is. All that matters is that it's ones and zeros. What happens with this magic box that I'll be explaining in a minute? It ends up turning as a modulated RF wave. Modulated, or modulation, is the key to what we're going to be talking about now. And it gets sent out as your RF wave, and it gets sent out through your broadcast antenna. And what happens when we receive it? We receive this modulated wave. It goes through our flipped round magic box, and then we hopefully get our demodulated data round. And we'll get these lovely ones and zeros. However, for the sake of this presentation, don't worry, acronyms, like I said, this isn't what you need to worry about. So the whole point of this is that our ones and zeros that come in end up being our ones and zeros that come out. This is the whole point of us trying to broadcast things correctly and good enough for us to see it on the other side. Like I said, acronyms, forget about them. So all of this, it doesn't matter. I just want you to focus on ones and zeros. This is all that I care about, is good ones and zeros coming in and ones and zeros coming in. So completely, just do not worry about that. Focus on ones and zeros. Okay, sorry, we've got to put our thinking caps on now. Okay, you should be able to follow this as long as you think clearly. Okay, you should be all right. So enjoy the next couple of slides. It should only be less than 4 minutes. Okay, Do you remember binary numbers? Anyone remember this from school? Okay, we have our decimal numbers, which go from 0 to 9. I'm going to make another video on this for those of you who aren't sure. There should be some other link near this video. 0 turns into 0, 0, 1 turns into 0, 0, 1, 2 turns into 1, 0, and 3 turns into 1, 1. Okay, this is binary, just more about 2 bits. Okay? Don't worry, I'm going to go through this very quickly. You don't have to worry. Now, what else do you remember from school? Do you remember a cosine wave or a cos wave? Do you remember this when you were younger? If not, look through your maths books when you were about 13 and you should be able to remember this. Our cos wave is this nice bucket-shaped wave. And I'm going to say this is 0. Blue, 0. I'm going to say that's a cos wave. And if I see a 1, a blue 1, I'm going to say it's an inverted cos wave. It's upside down. That's all I've done. Now, remember your sine waves as well? Slightly different. Look back at your school books when you were 13, Google it or whatever. And then you see a sine wave has this shape. So I'm going to say if it's a 0, my sine wave looks like this. And if it's a 1, it's going to be an inverted sine wave. Okay, look back over your books. You should be able to remember this. So, how is this helpful to us? What I want you to do is add these two waves together. So we got our cos wave and we add that to our sine wave. What does it look like? It looks like this. So our 2 highest points have made a high point here, the 2 lowest points have made a point here. We've got a different shaped wave. You see what I mean? This, I can go through something else. There's already another video that I've already done, which is linked to something called QAM, and this explains all this a lot better. And so just to do these quickly, we get basically our 4 different decimal numbers, we get 4 different waves. If you look at the red ones, there are 4 different waves. That's what matters in this. This here is known as 4 QAM, and you can check the other video that I've done on this. So, what's the difference? If I want to send out these binary numbers in this order, I only have to send these waveforms. This is what modulation is. You change the numbers into different waveforms, and they're represented in that way. And that's the end of the math section. That's it. Calm down. You don't have to worry anymore. Okay? Plenty more information like this is either on the internet, Wikipedia, Google it, or there's also the other video, as I've said before. Or just look at your maths books when you're younger. Okay, now moving back to the physical domain, which is what I want to do. I want us to get away from the theory a bit more in this lecture. So, I'm going to talk about now how the waves actually travel. So I'm not on about what's inside the waves, how they're actually moving. Something I'm not going to talk about is how they're bent. I'm going to talk to you about how they're absorbed, which is what we'll discuss now. And this is dependent on conductivity and the wavelength. These two you should remember from your physics classes as well when you were younger. Okay? Now, this is a Faraday cage. In case you're not sure what it is, I'm going to show you a video right now. You can see there's a guy who's inside a cage, and now there's a huge amount of electricity, and it's striking that cage. But the guy does not die. The guy's inside the cage, completely protected, as long as he doesn't touch the outside. What's going on here? What difference does it make? And why does it matter with regards to broadcasting? So, I want you to imagine that this is a solid plate of metal. No holes in it, just a solid plate. And we have some form of electricity. We have some form of electromagnetic power going in there. This gets conducted in the metal, because metals are a very good conductor. Once again, you should have learnt this at school, and go back over your books or Wikipedia this. Okay? So that's what happens when you have a solid bit of metal. Now, we're going to talk a little bit about wavelength and how this relates to the Faraday cage. So this time I want you to think this isn't a solid piece of metal, it's a nice cage with lots of holes in it. If my wavelength is big, okay, wavelength is the amount of space that it takes for the wave to oscillate. If my wavelength is big, then I'm going to find it's actually going to get conducted by my metal cage. What's the difference here? If my frequency was a lot higher, then I can find, so it's a shorter wavelength, higher frequency. For example, light or gamma radiation, for example, so X-rays or whatever type of high radiation you want. This would be able to penetrate the actual cage. It wouldn't protect the guy. If it was X-rays, too much of them, the guy would be hurt. Okay, so moving on. as you can see, penetration. Okay, this here is called the electromagnetic spectrum. Quite easy. We're on about wavelength here. We're on about the different size of the wave needed for it to oscillate. So it starts right down here on our radio waves. You remember AM radios, or remember long wave radios, which is where it's a bit more noisy. And then we go all the way up here, we pass through visible light, we pass through ultraviolet light, then we go to X-rays and gamma rays, we get to the real sort of dangerous stuff here, the things that can actually penetrate our bodies, which is why, if you understand, that's what the connection is here. Well, I'm going to focus just a little bit right now about how this affects us in our atmosphere. So, as I've said, metals are a conductor, but water and air are not. They're different. So this here, for example, is our atmosphere, which is a lot of water, a lot of air molecules, a lot of nitrogen up in the air. It behaves differently. So as you can see here, down at this area, there's a huge amount of space where actually it lets it through. This here is the section we use for satellite technology. Then if you go a bit further out, you can see some of the visible light get through, and then also there's other things. It's not a complete perfect filter, and this is a whole other chapter as well, which we can go through, which is to do with the physical idea of how waveforms travel. Okay, as I said, they don't behave in the same way. So, moving on. Technical difficulties here. Right, now I'm going to focus on even tinier bit of the spectrum. I'm going to look right down, round about this way. Okay, not the most accurate of diagrams, but I'm going to look right down here. So I'm going to open this up into this spectrum, and I'm going to focus now around sort of TV technology and the sort of frequencies, the sort of part of the spectrum that we use to help broadcast our signals. We split these up into channels, which is separate sections of frequency, which we assign for each TV channel, or for each mux of channel, but that's something way off. Just imagine that each one of these is separated in a different frequency. So this is our amplitude versus our frequency, so taken straight from that graph. What does it mean? Going back to the idea of waves, do you remember what we were talking about earlier on with our sine and cos? Well, that is different with time. What's the difference? I've color-coded this here, and you can pause the video and you can have a closer look if you want. Our yellow wave, for example, is roughly in the middle. And then if we've got our other waves, so say this green wave here, this is actually a lower frequency, so we're going a lot further down. We've got the blue one here, which is a higher frequency, so hence it's higher up that way. Okay, there's plenty more information on this as well. Remember, if you're not sure about this, please send me an email or just comment on this video and I'll get back to you as soon as I can. Okay, moving on. So now, I want you to think, how do we tune to the frequency? So imagine what we were doing when we used to rotate the dial by our hand on the analog. Well, what does it do digitally? So when we try and adjust it, first of all, so if this is our filter, it's trying to find channel 3. Okay, that was too low here. Oh, now we're moving a bit closer. Okay, we might be tuning it here. So this electronics is trying to talk to it. Oh, no, we've gone too high. Right, okay, so now it's got to move back. We're seeing the red one here, the filter, until finally we get it just right. And we're fixed. Now we would get our lovely picture. I think we're fed up of seeing the same video. Let's explain it in a little bit of a simpler form. Let's look at visible light. Do you remember from your physics classes? What is white light? If you add it all together, what do you get? It's the mixture of all of the colours of the rainbow. You add them all up in the same level, and you end up getting visible light, white light. So what's the difference? What other type of filter is there? What about, so hang on, let's just come back. Richard of York gave Battle in Vain, in case you can't remember that. Okay, so well, I want you to imagine that this is a piece of glass. It's a blue bit of glass, sort of things you see in churches. So when you can see straight through it, okay, but it's blue. What's happening there? What's the difference? Well, in this case, only the blue light is travelling through. Exactly the same idea. So we've got a filter, we've got some electromagnetic radiation or some electromagnetic waves going through our visible light, and we're only getting our blue wave out. This is exactly the same idea going through here. This is a filter. This is the whole plan. I'm trying to convince you here. Okay, now we're going to move on to more signal degradation. What do I mean by that? basically how the wave can get worse quality. How can we have problems with us actually viewing our TV, which some of you may have had. Okay, we're going to talk about terrestrial broadcasting. So that's similar to what I showed before. That was more about from our big broadcast antenna on our hill going straight to our house. Okay, a section of our spectrum, so as we showed earlier on with us tuning this channel. Okay, going back to the idea of a filter, we would like it to be a perfect filter, only looking at this channel, channel number 3. We don't want to take up any of the other channels. And so this will give us just our channel number 3. However, life isn't that good. It's actually quite impossible to build a filter perfectly. This is the whole idea of filter theory, and this is another video that I plan to make as well. But actually, we end up getting a filter that looks something like this. You get a little bit of other channels coming through. It's because of the way that metals are made, it's the way that physical properties are made. We can't do it ourselves. And so instead, we don't end up getting just our lovely channel 3. We end up getting our channel 3 with a little bit of everything else mixed in. What's the difference? So now, we get inside our TV, this is what we saw earlier on, and instead we end up getting a mixture of everything in, instead of just having the channel 3, which is what we wanted. Okay, now we're going to talk about something called sensitivity, which basically means a weak signal, so don't worry too much about the sensitivity. So, this will be a nice normal level, a nice clean signal that we've got going through. But, so, like I said, things are working well, our electronics are working good. Okay, so now what happens if we have a smaller bit of energy? Not enough, basically. So we've got this green wave. Maybe that's not enough for our electronics inside our TV to actually pick it up. So, that's one thing. That's one way that it can mess up our signal and not make our TV work properly. The noise floor, here's another thing. So this is what we were seeing earlier on. When you rotate the dial, you actually see this type of stuff. This horrible sort of grey, bubbly sort of thing. What's that? If our noise floor is quite low, if it's a small amount of noise and we've got a nice strong channel, it doesn't matter. So this is looking at our frequency domain, where it goes all the way across. And then here, it's properly tuned, and then we've only got a little bit of noise there. It's okay, our TV can get rid of that. What is the noise floor? Okay. So, it can be several things. One is it's coming from space, so from supernovas, from all these noise coming out in the rest of space, which is coming into our atmosphere, like similar to what I showed earlier on. It can be things coming from cities, so it can be your mobile phones, it can be whatever, your computers, loads of things. It can be things coming from the centre of the Earth, so your volcanoes, your lava, that gives off other things, not just heat, not just light, it gives off other radiation as well. And also, the thing that we can control the most is actually the noise that our electronics give off itself. This here, all adds up. Okay, so moving on. What's the difference here? Going on to the noise floor. So if the noise floor was too high compared to our signal, well, it would cover up all our channel we want, which would cover up all our wave we want. And then in the end, this might be too noisy to actually tell the difference between what is the noise floor and what is the actual signal. Our TV might not work for that. Okay, going to go one more thing. Echoes, what are they? Let's imagine this is a surface, so it's not a metal surface which would conduct it, maybe it would conduct a little bit, which I'll explain now. So imagine we've got our wave, it's not going in at a nice 90 degrees, it's coming in at an angle. Well, some of it gets conducted, as I just said, but some of it gets reflected off. It's a reflection of it. That's what an echo is. Same if you were to listen to yourself in a cave or anything like that. So what happens? Echoes, they can come off buildings, where we get a reflection, which both end up going to your house, which can then ruin our signal, and also we can get it coming off mountains as well, which is several problems we have in the real world. And also the other way is by having two broadcast antennas, which then also mix as well. So now, do you remember this sort of thing. If you were 15, you should have learned this in your physics lessons or your maths lessons. It's called superposition. This is what I'm going to explain now. So, technical difficulties. So, if we've got our one wave, wave A, and then if we've got our wave B, which is exactly the same size. So we have two waves exactly the same size. What do? Two waves? You add them together. Wave A plus wave B, because they're exactly the same, you end up getting one twice the size. Remember this from school? Superposition. Maybe you'll understand this and realise it's not that complicated. So, what happens if I've got one wave that is this size, and then I've got another wave exactly the opposite, exactly inverted. So I've got a plus wave and a minus wave. Well, they're going to cancel each other out. You're going to get nothing. And you can see the difference now. So you can either end up having a signal that's too strong for our TVs to understand, or our receivers, or being too weak because it could be messed up. This is a more better idea about what it is. So we can have two waves coming in, and this makes the sum of the two waves similar to what we talked about earlier as being a bit off from what we want, which can confuse the TV. Okay, now just to think, each wave isn't just one, each channel isn't just one frequency. It's actually a mixture of hundreds and thousands of different frequencies, depending on how you split it up. So, a real-life echo signal, so this is more of a perfect way for an ideal sort of channel. When we get some echoes and say this is a real-world example we've got where a receiver wasn't working properly, we end up getting a shape like this because they add and they take away and they destruct and they construct to each other. Okay. So now we're going to talk about a bit of a trade-off, a little bit more now, going into error correction coding instead. Basically, we get this. More protection we have, there's ways of protecting us against this noise, versus having less data. And obviously the inverse as well. So if we have more data, then we're going to have less protection. All this I'll explain. And these are several examples. So QAM, as I said, there's already another video on this, and then I'm going to produce other videos on code rate and also on the guard interval, what it is in more detail. There's plenty of information on the internet which you can read up about this. Okay, this sort of thing, sorry about acronyms, okay, is from something called DVB, Digital Video Broadcasting, mainly which is used in Europe, but also now it's starting to be used a bit more in the Middle East sort of area, and then also in some places in the South of America. Okay, and we get all these different types. So T2, which is New Terrestrial Broadcasting. I'm not going to go through this, it's acronyms, this is boring. Okay, but let's just look at cable. What's the difference between cable broadcasting and terrestrial broadcasting? Well, some of it is limited. So if we have a poor quality cable here, we're going to get a noisy sort of signal coming out of it. And if we've got fibre optic cables, which is really popular now, we've still got our houses which have our old copper cable in it. It doesn't go all the way to the TV. We end up getting a reflection, so like an echo. So imagine I've got information coming in. When I get to this point here, I end up getting some of the information coming through, some of the signal, but I get some of it and reflected back. Echo signal, remember what we talked about earlier on? Okay, for satellite, what's the difference there? So, obviously, to penetrate through our ionosphere, to penetrate all the way down through all that air, it's not as ideal as what we had before. You have to have a huge amount of power. And so we have a massive reflection, and also coming through all this air, and everything that messes up, clouds, rainstorms, everything, we end up getting a noisy signal that in the end comes to our house. So, what I'm going to talk about now, the trade-off. We're near the end of this presentation now. What I want you to think about, and this is another whole different subject, is how data is made of packets. So let's imagine that one packet is just 2 bits, 2 binary numbers, and makes this lovely waveform. Let's go back to the same idea of what we were thinking about earlier on. But what I want you to imagine is that some of these packets, some of this has been disrupted. Some of it has not been received by our TV properly. But some of it, as you can see, is doubled up. This is called a code rate of a half. They are doubled. So we only get half the amount of full data possible if we just set the whole thing cleanly. And we've got our noise, which has happened here. Luckily, our only packet 1 has been sent through correctly. Now packet 2 has been corrupted. So we're going to ignore that one, but luckily packet 2 was sent twice. Okay, packet 3, however, though, we've got noise all over there. Well, we can see this one here, it's slightly better, okay, even though it's all being disrupted. So we're going to take this one instead. Packet 4, we're really lucky that there's no disruption there. Packet 5, you can see one of them's been disrupted, so we can take that one. And packet 6 looks okay, so we're going to take that one instead. But now you can see that we have a near clear amount of data that has been passed through. It's been error corrected. It has used error correction coding. These are all errors, and we've corrected them. But what does this make? This makes one uncorrectable error, just by having this packet there. And these will get counted up by a receiver, and hence causes problems. Sorry. When we are testing, we use a stream. We use a type of video that is repeated again and again and again and again. And we do our different testing using the same signal. This is an example of one of them. There's many out there that we could choose from. This is the main one. So it's this fish which is moving along, lots of different colours, lots of things. So what's the difference? If we had a lovely clean signal, it looks like this. But if it's all corrupted, we might get something looking more like this. Something with lots of errors in it, a signal that isn't clear. This you might recognise maybe if you've got a bit of a poor signal in your house, in your TV. This is a typical problem that we get. And lots of people think their TV is broken, but actually it's just the quality of their signal. It's not the problem with the TV at all. If we remember our analog signal, so what's the difference? So if we've got signal degradation, okay, sorry about the big words, signal's gradually getting worse on this side, and this is the performance of the TV. Remember, it starts off pretty good, it's gradually getting worse. This is our analog picture. So this is our old-fashioned TVs. Gradually get worse, if you remember, lots of lines going through it, until in the end we've got noise, we've got no channel at all. What's a digital picture like that? This is the sort of thing that people aren't cottoning on to, and people think that their TV is just broken. We get a lovely, lovely, lovely clean signal until we get just on this point here, just this failure point, where we start to get this blocky sort of picture, and then in the end we get a black signal. The TV thinks this is too bad, this picture, I can tell it's wrong. So therefore I'm going to put a black signal in now. I don't want to get people watching a TV that looks like this, there's no point. And it tells this, for your information, because of the uncorrectable error count. It can tell when there's errors, so that's why it stops. So, thank you very much. I hope that's a good introduction of... Wait, please. I hope that is a good introduction of our electronics. Please wait. And if you have any comments, please put them down underneath the video or send me an email to robertjohnweber@googlemail.com. And finally, just for you to understand, one more thing. So zoom in on these if you like. So by going through this and by listening to me, you've actually gone through quadrature amplitude modulation, radio frequency propagation, packetizing data, resonant frequencies, the electromagnetic spectrum, impedance, superposition, filter theory, fault error correction, and additive white Gaussian noise. Congratulations, you have learnt an awful lot today. Like I said, don't be afraid to give me comments, and I look forward to hearing your feedback. So, thanks a lot, and take care. Bye.